Hi, I'm Chris Lopez.
Hi, I'm Ian Lorber.
Hi, I'm Rich Moretti, and this is our senior design project, All Spooled Up, team advisor, Dr. Ping. So the project description, we designed a machine that can melt crushed PLA waste and respool the material for reuse. Why this project was important, there's a few things to read off. PLA is a waste issue. It needs a controlled compositing environment. PLA would take 100 to 1,000 years to decompose in a landfill. PLA needs to go to a compositing facility, not a recycling facility. There are only 113 industrial grade compositing facilities in the US, and this project makes 3D printing a more sustainable source.
So our final design for our extrusion machine, we can see here the auger gearbox and how it's mounted. The auger, which goes through the heating chamber, and the heating chamber is wrapped up with insulation and Kento wire. The nozzle, and then the filament winding stage.
So this is one of the engineering principles and theories we use to develop the gearbox for the auger in the heating chamber and the gear train for the spool winding stage of the machine.
So another engineering principle and theory that we used was the concept of thermal resistance. The equation above shows us how to get the temperature from temperature 1 to temperature 6.
So here we could see the heating chamber assembly. All the way on the right, we have the 3D printed gearbox, which has a motor inside of it, which is driving the drill bit auger that will be pushing the melted scraps through the heating chamber and out the nozzle.
So one of our main concerns was, since the drill bit or auger is attached to the gearbox, which is 3D printed, we wanted to know the temperature at that point to see if it would melt that PLA. So we designed and set up a simulation in ANSYS to understand this temperature. So the way we set it up was our boundary conditions. So we first applied a constant temperature of 200 Celsius on the red part, which you can see on the left-hand side. Then the orange and the different colored sides have a convection coefficient of 16 watts per meters cubed Kelvin. And then the auger inside has the same convection coefficient. So our results were that our tip temperature only reaches up to 102 Celsius degrees, and this is not enough to melt the PLA for the gearbox.
So here we could see a video of the inside of the heating chamber. As you could see in the center, most of the PLA has melted into a viscous liquid, but there are some scraps that have not been melted completely on the outside walls of the heating chamber.
We found out that the optimal temperature to melt PLA is around 200 Celsius to 210 Celsius. We found the maximum auger speed to be 3 to 4 revolutions per minute. Although some chunks did not melt fully, we were able to maintain the internal temperature of the chamber at 200 Celsius.
For the future works of this project, we would need to further refine the extrusion and melting efficiency to ensure the PLA chunks are fully melted. Also, we need to add a sensor that can detect the diameter of the filament so we can ensure a consistent filament diameter. Once we can achieve a consistent diameter, this will allow us to compare the material properties to test the quality of the recycled filament. And finally, an oscillating mechanism would be added to the spool winder to ensure the filament is wound neatly. This will prevent the 3D printer from jamming while printing parts. Thank you for listening to our senior design virtual presentation.